Hey everyone, welcome back to probability theory. This will be lecture 4 of the course, and in this section we're going to discuss how to calculate the probability of an event using sample points. So we've certainly seen this approach in the previous section. We kind of hinted at it for sure. Some of the examples we did, we explicitly sort of used it, but we didn't lay it out ahead of time and then reference it and kind of go through examples where we're specifically doing a certain thing. So I want to spend a lecture doing that. So let's jump into it. We'll call this section 1.4 and then just calculating the probability of an event using sample points. And so finding the probability of an event defined on a finite sample space can be approached in two ways, sort of. So the first way is the way we're going to talk about in this section, and that's just what I'm going to call the sample point method. That's what we're going to talk about in this section. There's a second approach which is somewhat different, and that is what you might be able to call the event. You might loosely call the event composition method. We'll get to that later. We're going to focus on this one in this section, so we'll discuss this here. And then we'll come to this other one later. We need a little more. We need a little more machinery, a little more infrastructure before we can really address method 2. So we'll focus on method 1 here. And so, what is the sample point, so-called sample point method? What does that entail? Okay, let's just kind of write it out. So the first thing, and again, this is going to be fairly straightforward because we've sort of did this in the previous lecture, but I want to just emphasize it here. So the first thing we need to do is we need to list the simple events associated with an experiment. So we need to list all of the simple events associated with an experiment. So if you're flipping coins, you need to think about what the experiment itself looks like. If you're flipping 3 coins and your observation is the outcome of all 3 coins together, then you need to list out all of the combinations that you could arrive at. If you're doing something like we did in the previous section, where you have broken and working parts, for example, then you need to think through what all of those observations would look like and break them down into the simplest events, right? And so this can be this is the part that is very frequently kind of the conceptual part. You sort of take the problem that you're trying to examine and break it down into these simple events. And so this is kind of where things can go very drastically wrong if you're not careful. So be careful with this one. Sometimes it's straightforward, other times it can be very tricky. Okay, so once that's done, what do you do? Well, the next thing to do is once you have all of these simple events, you need to assign probabilities. So let's assign probabilities to all of these simple events. Right, and of course, we want to making sure that the rules of probability are adhered to. So namely, the probability of a particular event is greater than or equal to 0, and the sum of all the probability of the events in the sample space equals 1. Okay, right? So as we sum across all of the events in the sample space, simple events, they need to equal 1. Okay, so we've listed all the simple events, and then we've assigned probabilities. Okay, and the third thing we want to do then is we have an event of interest. We'll call it event A. We want to define event A as a collection of simple events. So define event A as a collection of simple events. Okay, so A will be, A is the event, then A is equal to, maybe we'll say E1 or E2 or whatever, En, some ... or En, right? So some finite collection of events. So A is defined as a collection of simple events. Okay, and then because we're talking about simple events, they don't overlap. What we can do is, step 4 then is to find the probability of A by summing across these simple events. So find the probability of A by summing the probabilities of these individual simple events. Okay, so probability of A then is equal to the probability of E1 or E2 ... or En, which we know is the probability of E1 plus the probability of E2 plus ... plus the probability of En. Okay, and so that's the method. And that's largely what we did in the previous examples. It's just that we didn't have this, hey, follow these steps to get to the answer. We kind of felt our way through it, and now what we want to do in this section is just make it more formal and do a few more examples that use it explicitly. Okay, so let's take a look at a couple of examples. Okay, so the first example is, let's say we have a fair coin being tossed 3 times. A fair coin is tossed 3 times. Okay, we want to calculate the probability that exactly 2 of the 3 tosses result in a heads. So find the probability that exactly 2 of the 3 tosses result in a heads. Okay, so what's step 1? Step 1 is to list all of the simple events, right? So now remember, what is the experiment here? The experiment isn't tossing a coin, it's tossing a coin 3 times, right? So the sample space is going to consist of things like this, H, H, H. That means first toss I get a heads, second toss I get a heads, third toss I get a heads. Okay, another element in the sample space will be HHT. Heads, heads, and then tails, right? So first and second are both heads, and the third toss is tails. Right, and so on. We can kind of go through this, HTH, and then let's do THH. Okay. And then we can do TTT, TTH, THT, and then HTT. Okay, and so that's everything. So step 1 was to list all the simple events. I should write these down just because I'm trying to connect this method. List all the simple events. Okay. Step 2. What was step 2? Step 2 was to assign probabilities. We want to assign probabilities to all of the simple events in the sample space. And so because this is a fair coin, it's balanced, we would expect each of these outcomes to be equally likely, right? So the probability of all heads is equal to, well, there's 8 things in the space, so it's equal to 1 over 8, right? And so on. And so kind of working through all these, you'd end with probability of HTT is also equal to 1/8, right? Another way to say it is that the probability of EI is equal to 1/8 for I equal 1, 2, dot, 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 8, right? So for all 8 events, the probability is equal and equal to 1/8. Okay, very good. So far, so good. Step 3 in this method, in this approach, is to define event A in terms of the sample space, right? So define A in terms of these simple events. Okay, so define A in terms of these simple events, right? And so what was A? Well, A was exactly 2 heads in 3 tosses. Okay, and so if we just kind of look at our sample space up here, we're really talking about this guy, and we're talking about this guy, and we're talking about that guy. 2 heads. HHT, HTH, or THH. Those are the 3 simple events that can lead to A. Okay, and so we can write that out. We can say that A is equal to HHT or HTH or THH. Right? Now, depending on how you want to, what kind of notation you want to settle on, whether you're fine just using it like this, or you want to call this, E2 and this E3 and that E4, that's totally up to you. That's, your choice. I kind of gravitate towards using the symbols like this just because it's more intuitive to me than relabeling everything as a E sub some number. But if you prefer that, that's totally fine. They're equivalent, right? Okay, so we've defined A in terms of the simple event. It is equal to the union of these 3 simple events. And then step 4 then is to calculate the probability of A by summing the probability of its simple events. So calculate the probability of A by summing the probability of its simple events. Okay. So what that means is that the probability of A is equal to the probability of HHT or HTH or THH, which is equal to the probability of HHT plus the probability of HTH plus the probability of THH. Okay, and then we saw up above that these are all 1/8, 1/8, 1/8. So this would be 1/8 plus 1/8 plus 1/8, 3/8. Okay. All right, very good. So as you can see, this is very similar to the examples we saw in the previous section, but here we're just being very explicit about the step-by-step nature of the approach we're trying to lay in here. Let's do another example. Okay, let's do one more example. And so this example says the odds are 2 to 1 that when A plays B, so tennis players named A and B in tennis, okay, A wins. Okay, so the odds are 2 to 1 that when A plays B in tennis, A wins. And so what does this 2 to 1 business mean? Well, 2 to 1 odds of A winning just means that A wins 2 matches for every 1 match that B wins. right? So that's all that means. And we'll use that information when we're defining the probabilities later, but that's just giving us a clue as to what the probability assignment looks like. So then the question is, suppose that A and B play two matches. Suppose that A and B play two matches. What is the probability that A wins at least one match? That's the question. All right. So A has a better chance of winning in any particular match. If they play two matches, what's the probability that A wins at least one of them? Well, you can just kind of infer from the setup here that the probability that A wins at least one match is going to be better than 50%. Like A wins two matches to B's one, right? So you can just kind of guess at the onset that A is going to have a better than average chance of winning one, right? Clearly. So let's go through the method though here. So what is step one? Let's list the simple events. Okay, and again, this can be the tricky part here, but well, in this case, it isn't that tricky. You got two matches, and really what we're interested in is the outcomes of the two matches, and the outcome of two matches together constitute an observation, right? So the sample space here is going to be going to look like this: A, right, meaning that A wins the first match and A wins the second match. Another possibility would be that B wins both matches. B wins the first match, B wins the second match. A third option would be that A wins the first match and B wins the second match. Right? And then the final option, the only thing left, is that B wins the first match and A wins the second. There's no additional options. Every match has some winner, we'll assume, right? And there are two matches, so this is everything that can happen. So this would be all of the simple events of this particular experiment. Step two, then, let's assign probabilities. Okay, now, because A wins more often than B, the probabilities of these events are not going to be all equal. Okay, now, technically speaking, we don't really have the machinery yet in our probability arsenal to figure out exactly what these probabilities are. So I'm just going to tell you, but we'll see later where this comes from. And so the probability of A winning both matches, given the 2-to-1 odds of him winning any particular match, is 4/9. Okay. The probability of B winning both matches, given that B wins one match to A's 2, is 1 in 9. Okay, and then the probability of AB or BA are the same. Probability of AB equals 2 in 9, and the probability of BA equals 2 in 9 as well. And so again, just to reiterate, I don't expect you to know where these probabilities came from yet. You have to take my word on it. This will be something we'll know how to deal with in a few lectures, but we just don't have it yet. But that's the probability assignment, a very reasonable assignment given the information. And step 3 then is to define. Here we'll say it's event E, just to keep the confusion from the E's and the A's and everything. So define the event E of interest in terms of the simple events. So define E in terms of the simple events. Okay, and so what did we say E was? E was the event of A winning at least one match. at least one match. And so notice here it says at least, right? So A could win one match or two, at least one though, right? And so what is that definition of E in terms of the simple events? Well, E would just be equal to AA. He could win both matches, that's at least one, or he could win just one of them, AB or BA. Okay, so you've got these three simple events, which the union of is equivalent to event E of interest. Okay, and then step 4 is where we actually calculate the probability. So we want to calculate the probability of E by summing its simple events. So calculate the probability of E by summing the probabilities of its simple events. Okay, so the probability of E equals the probability of AA or AB or BA, and that's equal to the probability of AA plus the probability of AB plus the probability of BA. And of course that's equal to what? AA is 4/9, as we see up here, and then the other two are 2/9 and 2/9. And so we can see that adding these up, we get 8/9. Right? So if A and B play 2 matches, the likelihood that A is going to win at least one of them is 8/9. So pretty certain, pretty atypical that A wouldn't win. Okay, very good. Okay, so that is the sample point method for calculating an event, the probability of an event. And I mean, so as you can see, it's kind of it's a straightforward approach. So this is very straightforward. It's a straightforward approach to identifying the probability of an event. Some common errors include, and I referenced the first of these, incorrectly identifying the simple events, right? The nature of the simple events, and then, as a result, failing to list them all. So incorrectly identifying the nature of the simple events, and therefore not identifying all of them. Okay, so this is why I say that step 1, where you're kind of thinking through the problem and thinking through what the simple events look like, and thereby what the sample space needs to look like. That can be the tricky part, depending on sometimes that's very straightforward, but very often it can be tricky. And if you mess that up, then there's no hope for the rest of the work. So be very careful there. Another error is that many times the sample spaces are very large. And we're talking the sample space, it's finite, but it could have still millions and millions of things in the sample space. And so how do we count all of those things? So another issue that comes up is miscounting the sample spaces. So many times the sample space is finite, but has many items, like millions, billions. Okay, and so just even counting the number of items in the sample space can be difficult. So mistakes are made. Just counting the sample space. And so that's a nice segue into the next section, right? In the next section, it will specifically call out different counting methods to help us with this. And so we'll actually be referencing briefly a field of mathematics called combinatorics. So we'll get into some combinatorics in the next section. Right, and these specifically, these counting methods from combinatorics will aid us in accurately enumerating the elements of interest in our sample space. Okay, so that is where we will end this one. We'll see you all next time. Take care.